In this lesson, we're going to be talking about Objective 8.3, Weak Acid-Base Equilibria. So the learning objective states that we should be able to explain the relationship among pH, pOH, and concentration of all species in a solution of a monoprotic weak acid or weak base. You will notice that the objective stated monoprotic, so we're talking about one singular hydrogen. We will not talk about diprotic or triprotic, so like H2SO4, well, that's strong. But anything with H2 or even H3PO4, for example, we won't be talking about anything like that, okay? I know a bunch of the colleges will talk about diprotic and triprotic. We may mention it, but this AP class is mostly focused on monoprotic acids and bases. And again, this objective is emphasized on weak acids and weak bases. So 8.2, we talked about all the strong acids and strong bases 100% ionizing. Here, we know weak electrolytes do not 100% dissociate into their ions. So we also learned that pH stands for power of hydrogens or potential of hydrogens, while P is that negative logarithm, okay? This objective, we will learn about something called Ka and Kb because the K will tell us if a reaction is favorable in the forwards or in the reverse direction. So if it was favorable in the forwards, K would be greater than 1. And if this was in the reverse direction, it would be K is less than 1. So let's just kind of recap of when we talked about equilibrium. So when K was greater than 1 in the forwards direction, we consume reactants to produce products. So here, a K that's greater than 1, this is a strong acid or strong base because the 100% ionization. So last objective, when we talked about strong acids, strong bases, their K values are very large because you consume the reactants, so they're limiting reactants to produce products, they're ions. That's why whatever the concentration of your acid, that was the concentration of its ions that when it was broken up. Now this objective 8.3 talks about Ks that are less than 1. This is in the reverse direction, favorable in the reverse direction, where we do not consume reactants, or you can say we don't consume reactants a lot, so we don't produce a lot of products. So here, this is the main focus of this objective because this talks about weak acids and weak bases, because these do not break up 100%. So weak acids, let's talk about weak acids first, and then we'll talk about weak bases. So weak acids react with water to produce hydronium ions. So here, remembering that weak acids are going to partially ionize. So if our weak acids are partially ionizing, we can't say that our HA equals hydronium. So here we'll put a cross through the equal sign. So here, this is why H3O positive is way smaller than our acid. So H3O positive is way smaller than our original acid. And again, it's because if our acid concentration was 1 molar and it's a reactant, it's not going to be producing any hydroniums. So the hydronium is going to be way less. So a way to fix this is we assign a Ka, A being for acids, because it partially ionizes. So we at the beginning of this unit talked about Kw, where Kw was the autoionization of water, because water is going to, at a small rate, break up into hydroniums and hydroxides. So I know it's weird because in Unit 7 we had Kc and Keq, where it talked about concentrations of any type of reaction. And we also talked about Kp, which talked about pressure. When it comes to our acid, we also talk about Ksp, the solubility product constant. That focused directly on salts dissolving. Here, Ka is specifically geared towards weak acids, Ka. So the equilibrium constant for weak acids is Ka, and you can search up any weak acid and it will have a Ka associated with it. Please note that we often can report Ka as a pKa, all right, which we'll talk more about. So this is how we would write the reaction of a weak acid dissolving in water, or you can just say it's in equilibrium with the water. We kind of talked about how to write this at the beginning of this unit. But here, how this is different than a strong acid is this part right here, the double arrow. The double arrow is indicating that you're going to have some of your reactants left over after your salt dissolved. So think of it as our acid is a salt and it dissolved. Here, you would still have some of it remaining, okay? So to write the Ka expression, we'll take hydronium multiplied by the conjugate base all over HA. So here to get a pKa, it is the negative log of Ka, all right? And again, when we use this P, this power of Ka, again, it's just a shortened version because we're going to get into some big Kas. So you're going to want to look at a pKa, okay? Just to look at it in a different perspective. One way that you can think of it is the smaller that pKa is, that is going to give us a stronger, in a sense, acid compared to a larger pKa is coming from a K that's very, very, very tiny, okay? Now let's talk about bases. So bases, weak bases react with water to produce hydroxide ions in solution. So just like weak acids, they partially ionize. So our base does not equal OH minus. Here, our hydroxide is way smaller than the concentration of our initial base. So here, the workaround with this is we assign a Kb, and again, Kb is for our weak bases because of it partially ionizing. So, like I said, the equilibrium constant for weak bases is K subscript B, often reported as pKb. So here, looking at this equation right here, this is the way that we will, so when we talked about strong bases, we did not include the water, okay? Because the water wasn't necessary because our bases have hydroxides. Here, not all of our bases will have hydroxides, so that's where our water will come into play. Because if you think about it, if this is your base and this is your acid, then your acid, based on Bronsted-Lowry, will donate a hydrogen, so you'll be left with a hydroxide in the products. So here, everything will be written with water as a reactant, strong acid, weak base, except strong bases. They will not include the water. So here, our Kb expression, looking at that reaction above, Hb positive multiplied by hydroxide all over base, and that leaves us with how to solve for a pKb, negative log of Kb. Now, one thing I want to note, these equations and these reactions are all found on your equation sheet, okay? So humor me right now, grab your equation sheet and you will see it in that section for a Ka expression and a Kb expression. Now, of course, it does not have the actual reaction itself, but it does have the expression, which you can put 2 and 2 together, how you would write the overall reaction, just looking at that Ka or Kb expression, okay? All right, so let's now talk about the relationship between Ka and Kb, okay? So you'll see on one of the last couple equations on the acid and base section, there's an equation that says that Kw equals Ka times Kb. So knowing what we know about pKa and pKb, we can make the assumption that pKw equals pKa plus pKb. Now you may be wondering, well, why can an acid, a weak acid, and a weak base equal Kw? That doesn't make any sense. So here I'm going to prove it to you and show you. So I do want to know that this is only true for any weak acid-base pair. So what that means, this either can be a weak acid and its conjugate base, or a weak base and its conjugate acid. All right, so make sure you leave enough room because I'm going to prove to you and show you what this is going to look like, okay? So I'm going to do my example based off HCN. All right, so HCN is going to be an acid because that hydrogen's found in front. It's going to be weak because it's not one of the 6. So here, if this HCN is an acid, I'm not necessarily saying weak or not. Here, if an acid releases hydrogens, then here the base pair would be Cn minus, okay? This would be considered a weak acid-base pair where they are going to be used interchangeably. Here, HCN, since it's an acid, once it releases, you have Cn minus. And then if we went the opposite way, where Cn minus as a base gains a hydrogen, we make HCN again. So here, let's write what HCN would look like in just a regular reaction, just HCN, the acid, just dissolved in water, okay? So if I have HCN plus water, here I know that this is my acid, so this is my base. And so knowing that HCN in this beginning part, okay, is my weak acid, we know that acids release hydroniums. So here, to finish off this reaction, here we will make Cn minus, that conjugate base pair. I should probably write conjugate. There we go. Conjugate base plus hydronium. So here I'm proving to you that your weak acid I should probably put states of matter. Our weak acid, HCN, releases hydroniums, okay? But it also made our conjugate base Cn minus. Now let's write this as the base first. So let's say we had Cn minus, the base, in water. So here, this is my base, this is my acid, and knowing that bases are going to release hydroxides as a product, okay? Here, our product, and knowing that our base is based on Bronsted-Lowry, is a proton acceptor, that acid H2O will release a hydrogen to the Cn minus. So here, we will get HCN plus hydroxide. So here, conjugate acid, and then we have our conjugate base. Sorry, I forgot to write conjugate acid above. So here you can see Cn minus and OH minus, okay? So, not trying to confuse you just yet, but if you look up the Now HCN, since that is our acid, disregarding the water, again, what these two reactions are saying is if you had HCN, the weak acid, and it's dissolved in water, it's going to be releasing some CN minuses and some hydroniums. So here the Ka found on line is 5 times 10 to the negative 10, okay? Now, CN minus, if you just had, the cyanide ion, and again, these are going to be net ionic equations, just kind of FYI. So CN minus might be really sodium cyanide because we could cross off the sodium. Anywho, CN minus, here, if that was dissolved in water, it would be producing some HCN and some hydroxides. Its Kb found on line is 2 times 10 to the negative 5. Now, one thing I want to note, and I apologize, I don't have enough room. If you actually just add these two reactions together and cross things off, don't do this on your paper, but I just want to show you. Here, if we crossed off the CN minus and we crossed off the HCN, and we added those two together, look what we get. I'm going to write this on the next page if you want to write it too. Just make sure you're paying attention up here. Here you get 2 waters makes hydronium plus hydroxide. So here, Ka times Kb will give us Kw, which is 1 times 10 to the negative 14. Oh, that says negative 4. Negative 14. Again, this is all true at 25 degrees Celsius, okay? So here, that is where this equation comes from, all right? This Kw equals Ka times Kb. And we have talked about the autoionization of water, okay? So these two reactions are used interchangeably based off water, but here it's just trying to prove you how all of these equations are related, okay? All right. Moving on to more of the real focus of this unit, percent ionization of a weak acid or base can be calculated. So here, what that's trying to say is for strong acids and strong bases, we know the percent ionization is 100%. But if we're talking about a weak acid, weak base, you can actually calculate the percentage of how much actually ionized. So here, for our acids, percent ionization will be hydronium over the original acid concentration times 100. And then for bases, you just take the percent ionization is hydroxide over the base initially times 100, all right? And then we can calculate since this is less than 100%. And you're going to be surprised over some of the problems we do, and you're going to see kind of how low these values are when I'm not really kidding that it's very, very, very less than the original. All right, so I'm going to give us some steps to doing ice table problems that require weak acids and weak bases. Again, you're going to treat it just like we've been doing with ice tables in Unit 7. But the whole thing is the goal is we can solve for how much actually dissociate into ions based off its K value. So first step is write the reaction of the weak acid or weak base. So here, if it's going to be a weak acid, I'm going to put WA for weak acid and WB for weak base, okay? Here our weak acid reactions will look like this, while our bases will look like this. All right. Next step, work on your ice table, okay? Write the reaction, plug in initial concentrations. Generally, it's going to be that initial acid or initial base. Next step, complete table for the E part in the ice table, okay? Now, because these Kas and Kbs, if you haven't noticed from the previous kind of HCN example, they're going to be very small. So you can assume negligible negligible X a lot in these problems, okay? And again, that needs to make sure that it's less than 1 times 10 to the negative 5 if we do that. Step 4, write the equilibrium expression and plug in E. Next, last step, solve for X. For acids, X will equal hydronium from your ice table. Or here, if you're doing bases, your X will equal the hydroxide. And again, this is all from your ice table. And then solve for pH or POH. I doubt you solve for POH, but it doesn't hurt to just do that, okay? All right, let's look at the first problem. What is the pH of a 0.075 molar solution of acetic acid? And they gave us the Ka expression. So let me zoom in right here. First step, write the reaction. So we have acetic acid. Here, always put water as the reactant, and it's going to be producing the acetate ion and hydronium. Now I'm going to complete my ice table. So here, this is 0.075. Water will always be an empty column, and you're going to have 0 and 0 of your products because this is before it was dissolved. Here, minus X plus X plus X, then plug everything down. So since our Ka was 1.8 times 10 to the negative 5, I'm going to assume negligible X. Okay, so here I'm going to write my Ka expression. So Ka equals acetate ion, hydronium, all over acetic acid. And now I'm going to plug everything in, okay? So we have 1.8 times 10 to the negative 5, X squared on top, and then 0.075 on bottom. Okay, so now we got to get X by itself. So here, I'm going to zoom in over here. Here, what's essentially going to happen is you're going to have X equals the square root of 1.8 times 10 to the negative 5 multiplied by 0.075. That's essentially what's going to happen. Here you get your X as 0.0016. So since X equals 0.0016, like I said, 116, my bad. Here, X will be the hydronium concentration, because look, this right here is this X right here, and that's what we're solving for, because this question wants to know the pH. So here, now I can do pH is the negative log of this 0.00116. Plug that in, you should get that the pH is 0.94. Okay, now you could solve for the percent ionization. I'm not trying to spend too much time on it, but I just kind of want to show you real quick. If you did percent ionization and you did hydronium 0.00116 and then divided by the initial acid of 0.075 times 100%, you're going to get the percent ionization as 1.55% ionized. So you have to think how small that is, people, because we know our strong acids and strong bases 100% ionized, and look at here, this only ionized almost 2%, okay? That's a small number. Okay, now let's look at this problem. We're going to be solving for the pH again, and we're working with something called NH3, okay? We have not seen this before. Now don't jump ahead and think, oh, I see a hydrogen, this is going to be a weak acid. Here, always look sometimes to the K off to the side, because it may actually kind of hint towards it being, you know, a K. It might end up indicating if it's a weak acid, weak base, but don't always assume that, okay? So here, Kb, this, again, is a weak base. So let's first write the reaction for this. So NH3 plus water. The ammonia NH3 will gain a hydrogen and be ammonium plus hydroxide. So here, ice table problem, let's plug everything in. 0.25, no to the water, 0, 0, then minus x plus x plus x, and then plug everything down into E. Here, since our KB is 1.8 times 10 to the negative 5, I can assume negligible x. So then let's plug everything into a KB expression. So KB equals ammonium multiplied by hydroxide over ammonia. So here, 1.8 times 10 to the negative 5, x squared over 0.25. So essentially what's going to happen is x is going to be the square root of the KB multiplied by the initial base. Sorry, I almost said acid. So here, when I solve for x, I get 0.002121, and that x is going to be hydroxide. Again, this x comes from right here, okay? So now, before we start getting ahead of ourselves, this is a hydroxide concentration. You can't go directly to a pH. So let's first solve for POH, and then we can do 14 minus that. So here, POH is 2.67. So then to solve for a pH, 14 minus 2.67, you get your pH as 11.33, which this does make sense because if this is a weak base, we should be at a pH that's greater than 7, which it is. All right, so I have one more problem, which I would love for you to do, but one thing I want to just note before you get started. We want to know the pH of a 0.15 molar solution of F1 minus. And they tell us the Ka of HF is 6.8 times 10 to the negative 4. So here, this is a weak acid, which means this has to be its conjugate base. So what you need to do first is solve for what Kb is, knowing that equation that connects Ka and Kb together, and then you can start approaching the problems. So yeah, this got you started. Why don't you pause the video, try this out yourself, then click play and I'll go over the answer. All right, so you should have gotten the Kb as 1.47 times 10 to the negative 11. So then, as I write my reaction of F minus plus water, I get HF plus OH minus. Here, plugging everything in and then solving for X, I get 1.49 times 10 to the negative 6 as the concentration of hydroxide. So taking the negative log of that, I get a POH of 5.83. So then 14 minus 5.83, I get a pH of 8.17.